Let's now look at some techniques for integrating trig. So we have our standard ones that we know. And so sine we know goes to negative cos, we know cos goes to sine, we know sec squared goes to tan. We know that tan, well, it's not actually on the actual table, but hopefully we remember to save ourselves some time. But if you don't remember, of course, tan can be rewritten as sine on cos. Then you have derivative on function, or minus the derivative on function, and you get minus the log of cos, or if you don't like negatives, you can make that the log of sec by bringing the negative in as a power. We're now going to look at sine to the power of n, or cosine. I'm just going to do sine to the power of n. Because they're complementary ratios, the technique's identical for both. So sine to the power of n. We'll start off with power of 1. Very tricky. Sine x, it's minus cos x. Okay. We then go to sine squared. And we've seen that one. So sine squared, we have to use our double angle results, but rearranged. So we get a half the integral of 1 minus cos 2x. If it was cos squared, it would be half the integral of 1 plus cos 2x. And we can integrate both of those. Okay. So we've seen both of those so far. Sine cubed, what to do? Going to rewrite sine cubed as sine times sine squared. Then sine squared I will change to 1 minus cos squared. But now I can do it by substitution. If I let u equal cos, then du is minus sine x. So I now have derivative times function. So I have minus the integral of 1 minus u squared du. And now we can just integrate and sub back in for u. So whenever I have an odd power, okay, what I'm going to do is I'm going to factorise sine to the power of 1 out. Because what that will leave me with is sine to some even power. Remember, we're talking about if it's an odd power. If it's an odd power, factorise out sine to the power of 1, I'm going to get sine to the even power. Now, sine to an even power, I can always write as sine squared to some power. And then the sine squared I can change to 1 minus cos squared, and then I can do my substitution, u equals cos x. So any odd power, I'm going to do that the same way. Factorise out the sine, change the sine squared to 1 minus cos squared. Well, what about an even power then? Even power, I'm not going to factorise out the sine. But I'm still going to use the idea that, hey, I can write it as sine squared to some power. So I've got sine squared squared. But now I'll use my double angle result. And so sine squared is a half, but of course the half is squared, so I get a quarter out the front. 1 minus cos 2x all squared. Then I can expand that out, and I've now got 3 terms that I can integrate. I can integrate 1, I can integrate cos, and we know a technique for integrating cos squared as well. So that cos squared there, I can rewrite again as a half of 1 plus double angles, so it's cos 4x. Now we can integrate everything, but I might just tidy it up because I've got 1 plus a half there, so that's 3 on 2. Let's finally integrate all that. And there we go. Now, whether you want to expand that out or not, I mean, that's up to you, how you want to leave that particular integral. So any even power, I'll do it that way. I'll rewrite it as sine squared to some power, substitute in the double angle result. And you're just hoping that the power's not too big. Because obviously if the power's big, we're going to have a long expansion and we might have to do that process over and over and again so I can eventually bring everything down to sines and coses. So sine to the 5 then, odd, factorise out the sine. So that leaves me sine to the power of 4, which I can write as sine squared squared. Sine squared I change to 1 minus cos squared. And now I can do my substitution. I think the odds are nicer myself. Expand out the 1 minus u squared squared. And there we go. Integrate and sub back in. And I can keep going and keep going. I'm going to stop there. I won't worry about sine to the power of 6. Okay. So the next one to look at is what happens if we've got a mixture? We've got sine to the power of something and cos to the power of something. vast majority of the time, we're simply going to substitute in u equals sine x or u equals cos x. Because if I've got a function which involves sine multiplied by cos, and sine's the derivative of cos, or cos is the derivative of sine, I can usually do a substitution and create a derivative there. So let's have a look at this one. Cos to the power of 5x sine cubed x. All right. The sine cubed, I'm going to change to sine squared times sine, but I've rewritten the sine squared as 1 minus cos squared. Okay. So what we basically do is we factorise out either sine or cos. Because again, in this case, both the powers are odd. So I'm always looking for the odd power. Now in this case, both of them are odd. And then I factorise out either sine or cos. Now I chose sine because it was the lower power. So I know that eventually my expansion is going to be easier. I could have factorised out the cos, and I would have been left with cos to the power of 4, which I could have written as cos squared squared. The cos squared I could have changed to 1 minus sine squared, but then I've got to expand out 1 minus sine squared squared. I'm going to get something longer I have to deal with. So the good idea to go for the lower power. So that's why I chose the sine there. And the sine squared that I'm left with, I've changed to 1 minus cos squared, and I can do my substitution, u equals cos x. So if we make u equal cos x, I end up with minus, because du is minus sine x dx, u to the power of 5, 1 minus u squared du. I've put the negative back in to make it look a little bit neater, but we get u to the power of 7 minus u to the power of 5. Simply add 1 to the power over the power, sub back in. Okay? So if they're both odd powers, then I'm going to choose the higher power to be the substitution, which means it's the lower power that I'm going to factorise out. Okay? So when I say the higher power, that's what I'm choosing for u. So in other words, the lower power is what I end up factorising out. So all right, that's if they're both odd. Well, I've got one odd and one even. Well, I'm just going to choose the odd one. Because again, I can pull out, in this case it'll be cos x I'm going to pull out. So I'll pull out the cos x. That leaves me with cos squared. The cos squared I can write as 1 minus sine squared. And now I'll do the substitution u equals sine x. And so I get u to the power of 6, 1 minus u squared. Add 1 to the power over the power. So that's easy. I don't have a choice there. I just go with the odd one. So it's the even one becomes the substitution, which therefore means it's the odd one that I'm pulling out the cos or the sine, whatever the case may be. All right, so they're pretty much done the same way. What if they're both even, though? So if they're both even, I can't do that. Because if I pull out, say, the cos x here, I'm left with cos to the power of 1. And that cos to the power of 1, I can't change to the sine. So I factorise, well, it's already factorised for the sake of this one, but I factorise and change the one of them to the 1 minus sine squared. Because remember I just said both of them are even. So if they're even, I can write them as sine squared or cos squared to some power. Now that sine squared or cos squared I'll change, in this case it was the cos squared, I've changed to 1 minus sine squared. And so then I can expand that out, and then I just use my techniques that we saw for sine to the power. Now I'm going to cheat. Oh, there's my answer. Because, of course, we did both of those just a few seconds ago. So I know the answer to sine squared, so I've just written it down there. And sine to the power of 4 we did, so I've just written it down there. Sort of explains why I bothered doing sine to the power of 4 before. And there it is, tidied up. Yep. So if they're both even, either change sine squared into 1 minus cos squared, b to the power of something. I've made my example there the easiest it could possibly be, of course, because it was just to the power of 2. But say we had, and it'll be a fair bit of work, but say you had sine, let's say the power of 4, cos to the power of 6. Okay? So the sine to the power of 4, I could change to sine squared squared. The sine squared I could change to 1 minus cos squared, and then I could expand that all out, and everything will be in terms of cos to the power of something. And then I used to use the different techniques and all the powers. So hopefully if we do get two even ones, the powers are very low, because it gets a lot of terms very quickly in that one. All right, well, let's have a look at tan or cotan. Again, they're complementary ratios, so it's the same technique. We'll just do the tan one. Integrate tan, well, we know that is the log of sec or minus the log of cos. But, of course, if you do forget, you could always rewrite tan as sine on cos. Do it that way. Tan squared. Tan squared I can rewrite as sec squared minus 1. And we know how to integrate sec squared, and we know how to integrate 1. So I just use my trig identity there, and we get tan x minus x. Tan cubed. All right. I've factorised out tan, but I've gone tan by tan squared. The tan squared I've changed to sec squared minus 1, and I've split it into two integrals. Now, the first integral, I've got tan times sec squared. So actually I've got derivative times function there, because sec squared is the derivative. So I could, if I use u equal tan x to u is sec squared. The second one is just integral of tan x. So I've got, eventually, there we go. So the tan x sec squared becomes u to u, which is a half u squared, subbing back in the half tan squared. Now, it doesn't matter whether it's odd or even. I'll always use that same technique. Here's tan to the power of 4. I'm always going to factorise out a tan squared and change it to sec squared minus 1. Because then I can always split it into two integrals. One, where I create a tan function times sec squared, which is its derivative. So I can always do u equals tan x. The second one then just reduces the power of tan. And I just apply the technique again if I have to. In this case, tan squared, I could change to sec squared minus 1 and then integrate that. So let's do a substitution for the first one. We get u squared du. And of course, from what we saw before, I know tan squared went to tan x minus x. And there's our final answer. And so every power of tan is done the same way. Okay. Sec or cosec. So once again, complementary ratios. Now we've got some fun ones to look at. Integral of sec, which of course we haven't done yet. We're going to use a technique, and possibly you would have thought of doing this as well. I'm going to multiply top and bottom by sec x plus tan x. It seems a logical thing to do. All right. Now, why do that? The top becomes sec squared plus sec tan. And what I've actually got there is derivative of a function. Because the derivative of sec is sec tan. You may remember that from when we were doing conics and we had to differentiate sec x. And derivative of tan is sec squared. So it's derivative of a function, so it's the log of sec plus tan. Of course, what's probably going through your mind right now is, how do you know to do that? And of course, the answer to your question is you didn't, but you do now. The reality is, I'm just writing log of sec plus tan. It's another one of those ones that I just remember. Sec x is the log of sec plus tan. Okay? If you do forget, hopefully you remember that clever little technique there of multiplying top and bottom by sec plus tan. Mind you, if you remember the clever little technique, you're probably going to remember it's log of sec plus tan. No. So there's sec, log of sec plus tan. By the way, what does that mean the integral of cosec is? Yeah, minus the log of cosec plus cot. Whenever you're integrating a complementary ratio, the answer will be the negative of the answer, but then you change them to the complementary ratios. So minus the log of cosec plus cotan. All right, sec squared. Strangely, sec squared is easier to do than sec to the power of 1, because sec squared is one of our standard integrals, and we know sec squared is tan. All right, are you ready? Hang on to your seats. We're in for a bumpy ride now. This is the fun one. sec cubed. Okay, I'm going to rewrite it as sec x times sec squared. Now, I've got a product of two things. One is not the derivative of the other. So I'm going to use integration by parts. Now, integration by parts. The u is something that when I differentiate makes it simpler. Oh, well, differentiate sec, we get sec tan. That's not really simpler. Differentiate sec squared, I'm going to get 2 times sec tan, so I'll get 2 sec squared tan. That's certainly not simpler. Or maybe it hangs on the integration then. If I integrate sec, I get the log of sec plus tan. So I can do that one. Or my other alternative is integrate sec squared, and that's just tan. That probably seems the easiest way to go. So I'm going to choose u equals sec, so du becomes sec tan. I'm going to choose dv to be sec squared, so v is tan. So we will get uv sec tan minus the integral of v du. So tan x times sec x tan x, I get sec x tan squared x. But my tan squared, I can now change to be sec squared minus 1. And if I expand that out, I get 2 new integrals. One of the integrals is something I can do, integral of sec x. It's the log of sec plus tan. Sec cubed. Oh, that was the original question. So I used that idea that I used yesterday, where now I'm looking at it, and I'm not looking at it and thinking of, oh, here's my working out. I'm thinking of it as an equation. So I can pick any 2 lines in there and say, well, this is equal to this. I'm going to pick the first line, which is the integral of sec cubed, and say, well, that's equal to sec tan minus the integral of sec cubed. Move the integral of sec cubed over. So I now know 2 times the integral of sec cubed is sec tan plus the log of sec plus tan. So we finally have our answer. Divide both sides by 2. It's a half sec tan plus a half log sec plus tan. So if it's sec to an odd power, I'm going to end up using parts in there to do that. Sec to the power of 4. Actually, the even powers are easier, because the sec to the power of 4, I can always extract a sec squared, that's even, leaving me with an even power, and an even power I can always change to 1 plus tan squared, and then I have derivative times function. So the even powers are much nicer. So u equals tan x, du is sec squared, and so I've just got 1 plus u squared du. So even power, so you can always factorise the sec squared out. It'll leave you as sec to an even power, and that sec to an even power, you can always write as sec squared to the power of something. Sec squared becomes 1 plus tan squared, and you got a simple substitution. I didn't bother doing sec to the 5. It gets a lot longer, but it's the technique of parts. Bring out the sec, leaving you with the sec to the 4, and oh boy, it's fun. It's fun. So, all right.